Hello everyone. So today we will study about voltage divider bias configuration in bipolar junction transistor. So this is a voltage divider circuit. As you can see, there is R1, R2, RC which is collector resistance, and RE which is emitter resistance. Here IC denotes the collector current, IE denotes the emitter current, and IB denotes the base current. VCC is the source voltage. To solve this circuit, we will simplify this circuit as follows. We can change the VCC into point voltage, and to solve this circuit, we will have to find the Thevenin's voltage and Thevenin's resistance. Further simplification shows that this circuit is similar to the emitter bias configuration. To find the Thevenin's resistance, we will have to find the equivalent resistance between R1 and R2. Since then R1 and R2 are in parallel combination, the Thevenin's resistance is R1 R2 divided by R1 plus R2. Now we have to find the Thevenin's voltage. The Thevenin's voltage is the voltage across R2. So voltage across R2 is R2 into VCC divided by R1 plus R2. Let's solve this circuit to get the base current. So we will apply the Kirchhoff voltage law in the input loop as follows, which is BTECH minus RB into RTH minus VBE into IE/RE. Since we know that emitter current is equal to beta plus 1 IB, so we can find IB as VTH minus VBE divided by RTH plus beta plus 1 into RE. Since IC is equal to beta IB, so we can get IC as beta into VTH minus VBE divided by RTH plus beta plus 1 RE. Now we have to get VCE, which is collector to emitter voltage. For this we will use KVL equation in the output loop. The equation we get is VCC minus ICRC minus VCE minus IERE. Since IE is equal to IC, therefore VCE is equal to VCC minus IC into RC plus RE. Now let's know about the advantages of voltage divider configuration and why it is mostly used. The voltage divider configuration circuit establishes a stable Q point by placing a fixed voltage across an emitter resistor. This configuration also has stable emitter current and collector emitter voltage. And this configuration also has high bias stability. That's all for the video. Thank you. In this lecture, we will learn collector feedback biasing, as the stability of operating point can be improved by introduction of feedback from collector to base, and this is what we are doing in collector feedback biasing. By introducing our feedback from collector to base, and first we will calculate the value of current IC and the voltage VCE, as they are the coordinates of operating point, and after this we will discuss the advantages of collector feedback biasing. IB is the current in this branch, IC is the current in this branch, and I want to calculate the current in this branch. Let's say the total current is I. So I will use the Kirchhoff current law at this node to calculate the current I. According to the Kirchhoff current law, the sum of current entering the node is equal to the sum of current leaving. So therefore I total is equal to IC plus IB. Now to get base current, we will apply Kirchhoff's voltage law in the input loop. We get VCC minus IC plus IB into RC minus IB into IB minus VBE is equal to 0. Since IC is equal to beta IB, we get IB as VCC minus VBE divided by beta plus 1 into RC plus RB. We also get collector current as beta IB. So collector current is equal to beta into VCC minus VBE divided by beta plus 1 into RC plus RB. To get collectors to emitter voltage, we will apply Kirchhoff's voltage law in the output loop. We get VCC minus ICRC minus VCE is equal to 0. Since I total is equal to IC plus IB, we get VCC minus IC plus IB into RC minus VCE is equal to 0. Therefore, VCE is equal to VCC minus IC plus IB into RC. Advantages of collector feedback. It stabilizes the operating point against the variation of temperature. It also stabilizes operating point against variation of biasing voltage and also stabilizes operating point against the beta value.